All right, so today we want to talk about main memory and virtual addresses. I put the slides just now on the website. Can you see it now? Yeah, okay, cool. So few things like your homework is uploaded there in the website too. We made a few changes on the homework, so make sure that you're seeing the Google Doc, the updated version. I also posted a video for rest of the things that we discussed last time on the cache. Please watch that before quiz 2 because it would be part of your quiz. We also talked about addressing and so on. That could be useful for your homework. Maybe I can just very quickly talk about it here as well. So, I mean, one thing that some of you were confused about like addressing was, in caches we typically store things in terms of blocks, okay? And blocks, initially we said that essentially block is just 1 byte, okay? So each of these blocks was 1 byte. And then together they create the cache line. So for example, if we have 4 of these, there will be a 4-byte cache line. And some people use the blocks and cache line interchangeably. So some of the references say the entire thing is 1 block, and hence it's 4 bytes. What we said in the class was we calling this smaller units blocks. So this is block for us. And this whole thing is a cache line, okay? So our blocks are essentially could be 1 byte, could be 4 byte, could be 8 byte. Typically, we said that it's 4 bytes or 8 byte for us. So block is the smallest unit in our cache, and then multiple blocks creates a cache line, okay? And then if you have multiple of these cache lines, then we have, what do we call a set, okay? All of them together create a set. In direct map, we only have 1, so 1 set is basically 1 cache line. In our set associative, we might have multiple of these cache lines to create a set, okay? So a cache line is combination of blocks. A set is combination of cache lines. And then a cache is combination of sets, okay? So when we say, for example, the entire cache is X amount of bytes, you first have to divide it into rows or sets. Then you have to go through and see how many cache lines we have in a set. Then you have to see how many bytes, how many blocks you have in 1 cache line, and then you will see how many bytes you have in 1 block, okay? So eventually you get to the bytes that you want. And there were some confusions in the lectures because we interchangeably use blocks and bytes together. I went through the slides and fixed that. So if you look at these slides now, you should see that basically that the notion of blocks should be consistent among all the slides. Yeah. So the question is, does the address point to a block? Yes. The address points. So what we read and send to the CPU is this. And that's why we said we typically using 4 or 8 bytes of block because the CPU gets the entire 8 bytes together. Still, if you want to have byte addressability inside the CPU, then the CPU has to internally, kind of like find the byte that they want from that 8 bytes. We didn't talk about that because essentially that requires another shift in the CPU address. There's difference between CPU address and cache address. But whatever we discuss in the lecture, in the homework, and in the quiz is always about the cache address. So we don't care about the byte addressability inside the CPU stuff. That's another shift that we don't care. Is that clear? So when you want to compute your CBS, just please use this notion. I updated the slides as well to kind of like, because initially we assume that blocks and bytes are just like, there's 1 byte per block, and then the CBS that we discussed makes sense. But if you want to use multiple blocks, multiple bytes per block, then we have to, like, adjust our CBS calculations. Okay. All right. So going back to what we said last time. So we talked about memory hierarchy, right? And we said that essentially the goal was to have a memory that was both fast and large. And we talked about, cache performance, the hit time, miss rate, miss penalty. We talked about replacement policy. We talked about how to improve each metric. And that's, the video that I posted is also talking about more extensively talking about each of these metrics. If you remember, we talked about few of them last time, but if you watch the video, you will see that we talk about more of them in more detail, okay? And this is basically what we will discuss in your quiz too. So end of the discussion about caches would be whatever we will discuss in quiz 2, and your branch predictors and BTB and control flow hazards and all those things. And as well as, out of order execution and all those things, okay? So that would be your quiz 2. Whatever we discussed today, that would be part of your last quiz in quiz 3, okay? Okay, so I talked about this. So let's start now talking about the rest of the memory hierarchy, especially about the main memory and the disk. If you remember, we said that essentially we have this, cache hierarchy where we have the CPU, we have the register file, which was on chip, very fast. Then we talked about, this rectangle here, which was our multiple level of caches. We talked about, instruction cache and data cache in level 1, and then L2 and L3, depending on the need. And we talked about, the structure, like data, direct maps, set associative, and so on and so forth. We talked about what would happen on a miss, and then how we bring things and so on. We talked about cache line and how we bring data from my main memory to the cache and so on. So let's talk about this second half of our memory hierarchy and see how things are actually stored in the main memory. How do we deal with the disk and so on and so forth, okay? So we usually, what we do as what we call main memory is, in order to make our life easier, we typically combine DRAM and disk as what we call the main memory. We will talk about what we call demand paging in order to kind of like, swap data between the disk and main memory. But we typically, when we say main memory, we're talking about the DRAM part and the disk part. But if you recall, the delay for accessing things from DRAM was much less than when we are accessing things from disk, right? So again, similar to the caches and main memory, we want to, access DRAM more often than the disk, but that would be the scenario in some cases. A big difference between caches and main memory is that data is always there in the main memory, so there won't be a miss in the main memory. It's either in the DRAM, or if it's not in the DRAM, it will be in the disk. So there won't be a scenario that's not in either of those two. If it's not in DRAM, we call it page fault. So I'll talk about it. But eventually, it's either on the DRAM or on the disk, any of those two. Okay. But you remember that there is a huge latency between DRAM and disk that we will talk about. Okay. So let's start thinking about how do we store things and how do we store programs? Yeah, question. The question is, if there is a big difference between DRAM and disk, why don't we have main memory or DRAM as another layer of cache? Essentially, that's what we do. So for us, the DRAM becomes the cache of the disk, and we will talk about that. Yeah. So let's start to think about, okay, a program. Where should we store the program? And generally, what's the interaction between main memory and the cache and our program? So essentially, if you think about the main memory, the whole point of the main memory is storing all of my program. And when I say program, I mean the data section of my program and the code section of my program. It's not just the code, it's data and code for every single program that I have. And And we typically have multiple programs when we are dealing with, right? So we store multiple things and maybe we use one at a time, but if you have like, multi-tenancy, we might have multiple cores at the time and so on and so forth. So if you're looking at our main memory as kind of, an array that starts maybe from the top to the bottom, then for example, ideally we want to like store program 1 in some part of the main memory, another program in another part of the main memory, and another program in another part of the memory. And this story can continue with whatever number of programs that we have. At some point, our main memory gets full, and that's where you cannot store more things. And that's what you have seen in your systems as well. At some point, if your hard drive is full, you cannot essentially download or put more things to it, right? The biggest requirements for these programs, if you think about, is we want to make sure that they are quote unquote isolated, which means we want to make sure that one program cannot affect and change things in another program. This is for two reasons. It's for security reasons, because, for example, if you download an application and your application starts changing things in rest of your things, that's definitely what you don't want to happen. And the second thing is just for correctness, right? So, for example, you're running you're listening to your music on Spotify, and then Spotify needs more space and it starts writing things in your browser program, so your browser starts to crash, right? So you don't want that to happen. If Spotify wants more space, more area, then your operating system or your hardware should be able to handle that. Or at some point, in worst case, only that application should be crashed, right? The rest of your application should remain intact. So we need isolation for security purposes, and we need isolation for correctness purposes, for quality of service purposes, right? For the security, we will talk more if you're interested to learn more about that in a separate course. But generally, we want isolation for correctness aspects of things, okay? And as I said, each program is not just sequence of code. It's code, it's data, it's stack, it's heap, and it's all those things that we need for a program. So when you're saying program, you're basically talking about process in our operating system terminology. So we have the code, we have the data, we have the heap, we have the stack, and all those things, right? So essentially, what will happen is that this program becomes like tiny spaces that each one is kind of like separate things. Maybe this one is code region, maybe this one is data region, and this is kind of like stack that grows, okay? So when you're talking about program, you're talking about these different regions. Another thing that we want in our system is we need shared spaces between programs, because you want to have isolations between your programs, but you also want the programs to be able to share things together, right? So for example, you want to read similar data for both of them. You want to use things like, standard libraries for all of them, so on and so forth. So you want to have some shared space somewhere in your main memory as well, so that this program and this program can read and write to it if need be, right? And then finally, you want to have some reserved space for your operating system, because operating system needs to read and write things into your main memory, and operating system does not have a dedicated memory for itself. All it does, the operating system, is just use the same memory. So it basically, your operating system also shares the main memory with the rest of your programs, okay? So if you think about these things, let me see if I have it. No, I don't have it here. So your main memory is basically going to be kind of like, some programs, some parts reserved for the operating system. These are the programs, and maybe like another part here that is shared among these different programs. So we basically have multiple different regions in our system, right? So that's ideally what we want. And let's see how we can actually, implement this in real systems. So this is what we usually call memory management, or main memory management. In the past, the early days, we only had one program. We didn't have an operating system, and we didn't have shared spaces. So that's why we could have, simply and easily just assign the entire main memory for one program. So we didn't have the problem with isolation. We didn't need to do main memory management and so on and so forth. But modern systems, as you know, now use many different, programs. They use, multiple operating system if need be. So we need to kind of come up with mechanisms that we can kind of manage and isolated different programs from each other, right? So, okay, how do we share this? How do we achieve this? The first option that might come to your mind is, okay, why don't we statically, partition the memory into batches or parts and say, okay, this part is for program 1, this part is for program 2, this part is reserved for the main for the operating system, and so on and so forth, right? So what all we need to do is kind of like, enforce the isolation that we want. So basically, we're going to say that, for example, from this part down, this is everything that relates to program 2. And from this part up, maybe until this part, this is for program 1. And maybe this part is reserved, for example, for the operating system. Okay? So we need two things that basically kind of like, help us to implement this idea correctly. We need protection because we need to make sure that if program 2, if program 2 decides to access something in this region, our operating system should be able to block that. So we need protection. Another thing that we need to do is what we call location independence, because if some other day we decided that program 2 should be moved, for example, to here, so this side, so like, shift a little bit up or down, depending on how we want to statically, schedule this, our program still should work, right? Because it shouldn't be like, just dependent on this part of the memory. It should be some continuous block of the memory, and it should be working depending on, doesn't matter where we start and where we end, that program should still work, right? So we should be location independence in terms of the address of the memory. In order to kind of provide these two mechanisms, the first one, we need to basically check the bounds. We need to define, this is the beginning and this is the end of program 1, this is the beginning and this is end of program 2. And if somebody wants to access the memory, the operating system should check the bounds and say, okay, if you are above this bound, you're not allowed, for example, to access the memory, and so on and so forth. And for location independence, we already did that for many other things. We're going to use the base plus offset technology, right? So basically, all we need to change, if we change for example, program 2 in some other part of the memory, we just need to change the base. Everything is based off that base, right? So these two things basically kind of creates this type of addressing, where our address that comes from the CPU is going to be added with what we call a base register. And this would be what we call a physical address, the address that we're actually going to use in order to access the main memory, okay? So for example, if I move this program to the higher parts, all that changes this base address. So this base address, for example, is here. Now it moves to here, right? So if the base address, if I move the entire thing up or down, all I need to do is just the beginning pointer should also update it, okay? So that's just one register per program. Also, that's all we need, right? So if I change that base register, everything else would be in an offset to that base register. Another thing that we do is we're going to check the bounds with what we call a bound register, where essentially we're going to say that, okay, if, for example, program 1 is supposed to access memory addresses from 0 to 100, if it tries to access 101 or 200 or 300, we're just going to compare it with this bound register and say that, okay, you are above or beyond, above or below this bound, and you're not allowed to access that. So that access should be blocked. So we basically should not return the value. That should go into some form of what we call an exception or interrupt, and that should be handled by the operating system. That's where you're going to get your segmentation fault and so on in your program, mainly because you're trying to access somewhere in the memory that you're not allowed to, and then the operating system will block that and will crash your code. okay? So basically all we do is that our CPU address is essentially translated in what we call a physical address, and physical address, the actual address that goes to my main memory. In order to translate that for a static partitioning, all we need to do is adding it to some base register, and also checking the bounds to make sure that this program is indeed is allowed to access that part of the memory. Any questions so far? Okay. So this is the notion of address translation. So we usually call the CPU address the logical address, and what we actually access in the main memory, the physical address, okay? And for static partitioning, all we need to do is just add the base register to the logical address in order to get the physical address. That's all we need to do, okay? Another name for logical address is the effective address or the CPU address, okay? So CPU address is the address that we deal with in our programs, right? And that's the one that CPU sends to the main memory. It goes through the cache. It's a miss in the cache. Now it comes to the main memory. In order to access the right, line in my main memory, all we need to do is just adding this to my base register. How do we share the libraries or having a shared parts? We can have another base address for the libraries, and we can allow the bound checks to allow people programs to read that base address as well, okay? So basically what happens is that program 2 is allowed to access things from this bound to this bound, and also allowed to access this bound and this bound. So we basically do 2 checks, okay? And in both cases, we need to use the right base address. So basically the addresses would be either, for example, if you're starting from down, would be base plus some offset, or would be base plus some offset, okay? And this libraries, we might ask, like, what type of library are we using? So all these, like, printf, scanf, all these SCL libraries that you use, they are all basically storing somewhere in your main memory. It doesn't make sense for every single program that you're using, for example, printf, you just put it as part of your program, right? You're just wasting the same code a lot of time. You're just replicating that code. So what you can do is that you can use the standard libraries, storing all of them together somewhere, and then it just always access that part of the memory, right? So this way you're saving a lot of space. Okay, or if these 2 programs wants to talk to each other, they can use this shared space to, like, read and write things to part of it. Okay, and then the operating system itself would be also a program itself. So the operating system is, if you think about it, is a software itself. So what we do is that we, reserve part of the memory to store the operating system. Of course, none of these programs should be able to access the operating system, but the operating system is essentially able to access any part of the main memory that it wants, right? So it's privileged, so it can actually access everything that the operating system wants, okay? So that's the story with, like, partitioning the program statically. But you might ask, okay, what will happen if we decide now to add another program to this main memory? So the problem is that, if you have space to kind of, like, fit this new program, then you will fit it. But the main issue arises when this program is bigger than what we have available, okay? So in this case, we need to kind of decide what to do with the rest of the program. Should we kind of squeeze them, move them? What should we do with them, right? The second problem is, what if one program wants more space or less space? Like what if a program 1 wants to grow? What should we do then? Should we change program 2? Should we just not allow program 1, and so on and so forth, right? So these are the 2 major issues with just static partitioning of my main memory, because especially this would be a big issue in real systems, because we're gonna keep adding and removing programs in our main memory, right? So obviously the option 2 would be, instead of doing these things statically, we should do it dynamically. So basically, based on the demand, we have to kind of, like, find different areas in my main memory, and then try to, like, assign specific program to that part of the memory. And in order to achieve that, we need to kind of, create what we call blocks in our memory, and then assign these blocks into each of these two programs or multiple programs. We call this fixed size block a page. And what we're gonna do is basically we're gonna divide each programs into multiple pages. Think about a page as, like, 4 kilobytes of data or 100 kilobytes of data, whatever. It's just a fixed size that typically just follow for every single program. And then what we're gonna do is that we're gonna divide each program into pages. So for example, if one program is 1 megabyte, we're gonna divide 1 megabyte to the size of the page, let's say 4 kilobytes. And then we're gonna have that many number of pages for one program. For the other program, it might be smaller. So in that case, the number of pages that we're going to use for that program might be smaller, right? So this way, we don't need to kind of, like, assign a rigid size for each program. Now we have the flexibility in order of block size or page size to assign as many as pages or as less as pages we need for each program. Okay. So as I said, each program is typically 4 kilobytes. That's typically standard in most of the operating systems, and that's what we're gonna use in our course as well. And in order to have the byte addressability that we want from the main memory, basically the lower 12-bit address of our physical address is usually what's called page offset, which basically, since we have 4 kilobytes of data, we need 12 bits to access every single bytes in this page, right? So that's why usually the lower 12 bits of address is always called page offset, and that's just to address within one page. The rest of the address is just for addressing different pages. Okay, so it's similar to the notion of blocks and rows in our caches. For pages, we do page offset, and the rest of it is just what we call a page number. Okay. So if you're doing this, if you divide the programs into pages, then we basically can have a main memory and scatter these pages around. Because remember, we want to assign things dynamically. So it's no longer we say, okay, this portion of the memory is program 1, this portion of the memory is program 2, and so on and so forth. What we're going to do is that we're going to divide the memory into pages, as you can see here, and basically start from the top, say, whoever wants one page, here you go. This is the second page, this is the third page, and so on and so forth. And what will happen is that you will see that your pages will be scattered around in your main memory. So for example, your program 1, page number 0 could be here, 1 could be here, 2 could be here, 3 could be here. Same story for program 2 and same story for program 3. And then your operating system could also have pages scattered around. But we can also do the same reserving, and we can do the same sharing. So for example, we can say this many pages are shared among all the programs or between these 2-3 programs, and so on and so forth. Okay? So that's what we do in order to make our life easier. And you can see that, if I need more storage for one program, all I need to do is find an empty page and assign it to that program. If I want to assign a new program, completely new program into this memory, all I need to do is finding all the empty pages and say, okay, this page, and this page goes to you, and then you can run your program. Okay, so you're basically, creating a smaller granularity in our main memory, and with that, we're gonna be able to, dynamically add and remove things. And if a program finishes, all we need to do is finding those pages and basically invalidate those pages. So for example, if the green one, program A, finishes, all we need to do is say, okay, these pages are free from now on. If a new program comes in, we can just, provide those pages to that new program. Okay? Any questions so far? So the question is this only in main memory, or is it goes to the disk as well? Yes, disk is also doing the same thing. So for now, consider this big array combination of main memory and disk. Okay.
like some page number, like which date it is. Like you use the over 12 bits, like find which byte in the page.
Yes. Yeah, it should be. It's byte basically, or yeah, it's page offset. Or basically bytes. So within a page, since the page is 4 kilobyte, what you want to do is saying that, okay, this is the address of the page, but within that page, I want that byte or this byte. So I need 2 to the power of 12 or 12 bits to be able to address all those possible, parts in my, for example, if my page becomes 1 kilobyte, then I need 10 bits. If my page becomes 8 kilobytes, I need 13 bits and so on and so forth. But 4 kilobytes is usually standard, so that's why you typically just need 12 bits. Okay. So as I said, the pages can be scattered, and we typically have each of these is 4 kilobytes. Okay. The reason that why are we choosing 4 kilobytes, why not less and why not more? It's depending on multiple things. Typically just because we ran one bunch of different applications and saw that this is the right balance between page size. Later on, we're going to discuss what would happen if you use smaller or bigger page size. But you can probably guess that it's very similar to block size in our cache. Bigger page will pollute our main memory. Lower will not use the locality that we want. So 4 kilobytes is kind of like, a good number to kind of fix this. Okay, so now that we understand the paging and that's what we use in our modern systems, let's talk about, okay, how we actually implement the paging. And the biggest problem with the paging is now that the addresses and the pages could be generally scattered anywhere in my main memory. So for example, if a new address comes in for program A and program A wants to, for example, read that byte, how do we know that where this address is actually stored in my program? Because this is an address that they think it is, but in reality, for example, this page is stored here. In other cases, the page could have been stored here and here. So basically, there is a disconnect between what we think the address is in our main memory, in our processor, versus where we actually store that address in my main memory. Okay, and the biggest problem would be, okay, how do I find and how do I understand where these two addresses connect to each other? Okay, so in order to fix that, we use what we call a page table, a mapping, a table that kind of keeps track of what is stored where. Okay, and what we need to do is basically having a table for every program, that within that table, there are rows, and each row is basically the page number. So for example, if this program has 4 pages, we're going to have a table with 4 indices. And within that index, we're going to save the beginning of that page in my main memory. So P0, P1, P2, and P3. So P0 would be basically here. P1 would be basically here. P2 would be basically here. And P3 would be basically here. So we're going to point to the base address of the main memory where this page is stored. And if we have n programs, we need n of these pages, and the number of entry in each page table would be the number of entry, the number of pages that that program has. If the program has 100, we need 100 entries, each one storing 1 value. Okay. So these P0, P1, P2, and P3 are what we call physical addresses that points to the actual part of the main memory, okay? So what we need to do is that once this address comes, so this is basically the address that's coming from the CPU, we need to go first to my page table to get this address, and then use this address to actually, access my page, okay? So we need to translate the CPU address to the physical address the same way that we did it for static, partitioning scenario. But this time, this translation requires some page lookup, right? So we need to go to some table and then find that number, and then go to my physical address. In the static part, it was just a simple addition. Here, we need to go to that table and read that value, okay? So this is what we call virtual address versus physical address concept. The virtual address is the address that we think that we have in our CPU. So each program can have a bunch of different addresses. We say, for example, go to 0x100 or go to 0x200 or whatever. In reality, where this address is, where this data is actually stored, depends on how we are actually, how the operating system put things in my main memory. It could be in anywhere in my memory, because essentially it's just depends on where that page has landed, right? So we need what we call a translation between virtual address, the address that we have in the CPU, versus the physical address, which is the address that we actually store things, okay? And what we do is, now that we have the virtual address, then we can completely disconnect each program from the other program. We don't need to reuse address. You don't need to have unique addresses on the virtual domain, because all we need to do is, for every program, we need a table, and these addresses could start from 0 to whatever number that we want. And then for the separate program, we can start from 0 again, and then go all the way down. So our virtual addresses for every single program doesn't have to be exclusive. They can all start from 0 all the way to whatever number that it needs, because these physical addresses needs to be exclusive, because these are actually where things are stored in my main memory. So this address here and this address here cannot be the same, because these are two separate parts of the memory. So they have to be different. So our physical addresses can be different, but our virtual addresses can be the same. This could be 100, this could start at 0. This one also could start at 0. But the difference is that this is program 1, this is program 2. So the operating system knows which one is which. So if it's program 1, we need to go and check the page table for program 1. If it's program 2, I need to go and check the page table for program 2, right? So basically, the idea is that our virtual addresses could start from 0 to whatever number that we want. And for every program, we can start from 0. We don't need to keep track of, which virtual addresses this program is using. I need to use another virtual addresses. You don't need to do that. You can start from 0. All you need to do is your physical addresses should be unique and should be exclusive to each part of it. If you translate that, then you will have the correct address in your main memory. And this basically creates this illusion for each program that each program thinks that it can access the entire main memory, right? So your program can start from 0 and go all the way to 2 to the power 31 minus 1 if it's a 32-bit address, because it thinks that, I have all the addresses in the world that I want to. In reality, though, that this addresses, some of it are occupied. So we kind of do the translation and move things around in the background so that memory can be accessed correctly, right? So basically what we will see is that each program sees a large, private, and uniform memories. Addresses start from 0 all the way to the end. It thinks that all the addresses is yours. But when we are doing the translation, you will see that things are interleaved and things are moving around depending on how the operating system handles this. Does that make sense? Any question here? Okay, so this would be kind of like a graphic from virtual to physical. So our addresses, we usually use it with V0, V1, and so on. These are the virtual pages. They go to the page table for each program. We get the physical address, and then this physical address points us to the actual place that this page has been stored, okay? So our life cycle is basically when you're writing a program, we are dealing with virtual addresses. The virtual addresses goes into the physical addresses. Then the physical address is the one that's used for accessing the main memory, okay? And if you think about programs, this is what we think the programs look like. So we think program A has access to the entire 2 to the power of 32. And basically what we do is we typically divide each program to some reserved space, code, data, heap, and stack. And then the same story goes for program 2 and program 3 and program 4 and so on and so forth. And all of them, these are all virtual addresses that we use. If you're, for example, using some virtual address here, this virtual address has to be translated in some unique physical address. And that's when we're going to actually access our main memory based of that. Okay, and this story repeats for every program. The question that you might ask is, okay, then how are we actually, mapping this into a real physical address? Especially, for example, let's say your physical memory is only 1 gigabyte or 2 gigabytes, and you're thinking that you have the entire 2 to the power 32. So how does this actually maps? In reality, what happens is that programs doesn't use the entire 2 to the power 32. It only use portion of this code region. It's only use portion of this data regions. Okay. So although it thinks that it has the entire memory, in reality, what really occupies is just a tiny portion of my physical memory. Okay. And the same story for program 2. So program 2 also stores a tiny portion and so on and so forth. There will be a point where the number of programs will be so large that your entire physical memory becomes full. And that's where your memory going to get full and you can no longer, start a new application, right? You get segmentation faults, you get exceptions and so on. But in reality, in most of the cases that you can see, you can run 100 different applications all at the same time. Although all of them thinks that they have the entire memory for themselves, in reality, they only occupy a small portion of each memory, maybe a few megabytes, kilobytes here and there. Okay, so that's why how this in reality is actually being used in physical memory. Although the physical memory is smaller than 2 to the power 32, and there are multiple of these 2 to the power 32s, in reality, each of them only use small portion. Yeah. Mm-hmm. So the question is, when we are using a variable in an address, is this the address, the virtual address, or is it the physical address? In most of the cases, that's your virtual address. So for every program, that's the address that it thinks that it's there. So it's virtual address. And that's why it's like a 32-bit value, because your main memory could be even smaller than 2 to the power of 32, right?
How does this affect locality?
So the question is, how does this affect cache and locality? Remember, pages are still 4 kilobytes together. So we store 4 kilobytes of data together. So that's where we're going to get that locality, right? So we're not going to divide it into bytes and just scatter bytes. That's the reason that we have 4 kilobytes. So 4 kilobytes consecutive data is always stored together. So that's why you get, I mean, if you access arrays like, multiple index of an array, then it will be in the same page altogether. So you will get your locality. All right. So this would be basically your virtual to physical address translation. So your virtual address is, for example, a 32-bit number. Okay. The virtual address is divided into 2 parts, into a page offset and into a virtual page number. The page offset, if you remember, I said it's the lower 12 bits that if you have a 4 kilobytes of data, you want to use that 12 bits to kind of access the bytes that you want. So your page offset doesn't need to be translated because that's basically the offset to the beginning of the page. What you need to translate is this second portion of your virtual address, which is the virtual page number. So for example, if this is 12 bits and your address is 32 bits, then what you need to translate is this 20 bits into the physical address. So this 20 bits goes into the address translation, which is basically goes into your page table. And what you're going to get is the physical page number. How many bits is that physical page number? Depends on how many bits how many rows you have in your main memory. If you buy a main memory that is 1 gigabyte, you're going to have the log2 of that that size of the memory as the number of indexes that you're going to have. So that's hardware dependent. For one hardware, you might have more main memory. For the other hardware, you might have less main memory. So this size, it depends on that. This page offset always remains 12 bits because we usually just go with a page size that is 4 kilobytes, okay? So just to give you some numbers, for example, if we have a 32-bit addressing mode, our virtual memory size is essentially 4 gigabytes. We think that every single program has 4 gigabytes at their disposal. Let's say, for example, we buy a piece of main memory, a DRAM that has 256 megabytes. That means that we're going to have 2 to the power 28 bytes. And our page size, let's say it's 4 kilobytes as the standard. So if you think about the number of bits, we're going to have 32 bits of virtual address. We're going to have 28 bits of physical address. We're going to have 12 bits of page offset. So our virtual page number is going to be 20 bits, and our physical page number is going to be 16 bits. Okay, so if I go back here, this would be 16. This will be 20. This will be 12. And this will be 12. Okay. So this page offset translation gets a 20-bit input and then give us a 16-bit output. Okay, so let's translate that into that one. All right. But this is just one one configuration. You might have bigger physical memory, you might have smaller physical memory, and so on and so forth. If you translate this into 64-bit addressing mode, then you will have more page numbers and so on. Does that make sense? Any question here? The question is, does the page table fits in the single line of memory? We're going to talk about where we're going to store the page table. That's a good question. Whose job is it to do that translation? It's the operating system. It's the hardware's jobs. So basically, the hardware. I mean, the page table are stored in the hardware. The operating system is on it to kind of orchestrate this. So the address comes, the operating system just forwarded to the page table. All right, so this is basically your page table. So what we do is this virtual page number is basically an index. Think about this as a direct map cache, similar to the direct map, that basically each line is just one of these pages, right? So whatever this number is, we have that many entries here. If, for example, this is 2, we're going to go to 1 and 2 to the second one. If it's 4, we're going to do the fourth one, and so on and so forth. And then we're going to store the number, the physical page number here. So this value is basically the value that goes here. This is the 16-bit value that we are storing here, okay? And the page offset just directly goes into my physical address, and this is what we're going to get from the physical address, all right? And if you remember, I told you that for every program, we need to have a separate page table, okay? So this page table repeats for program A. We have another separate table for program B. We have another separate table for program C, and so on and so forth, okay? So there will be multiple programs. Each one will have their own page tables, okay? We typically also add additional flag or auxiliary information in each page table. So these flags are basically help us to kind of like, know, for example, who is the owner of this page, whether this page can be read only or write only, and so on and so forth. Okay, so your page table doesn't only store the physical page number. Typically, it also stores some form of a flag, a few bits here and there as well. We will talk more about these flags, but simple things is whether this page is read-only or not. For example, we'll have a flag for read-only. If it's 1, it means that you cannot write to this page. You can only read from this page. Or, for example, if you want to have a page that is shared among multiple processes, you can have a bit for saying that this page is shared among multiple processes and so on. So in order to kind of like get that information on the fly, we can have that in my page table. So whenever I do the translation, I also get that information about the page, and that way we can enforce correct execution. Yeah, so the question is, if you have these flags, essentially this is going to affect the size of my page tables and the size of my physical page number. Yes, if we say that this row, the number of bits in this row is constant, then if I add more flags, then I will have less physical page numbers, right? Typically what we do is we make this, so this part is constant, because this is relevant to how many rows you have in your main memory. Depending on how many flags you get, your rows grows or shrinks, okay? So for example, if you need 10-bit flag, each row in your page table is number of physical page number, whatever it is, plus 10, okay? So So yeah, so what I did here is still the same. What we're gonna do is that here we're gonna have a bunch of flags as well. So this page table gonna be this line. So basically, let me actually show it here. So this would be this plus some auxiliary part for flags. Your page table just grows. All right. So now that we know this, then the biggest question that someone also already asked is, where do we actually store these page tables? Because the page table itself seems to be something big, and we need to store it somewhere in my system as well. And the idea is that we actually can store the page table within the page table, within the main memory itself. Okay. So what we do is essentially every single memory accesses becomes essentially effectively two memory accesses. The first memory access is for going through the page table and bringing the physical page number. That's the one that handles by the operating system. The second access would be the actual access at bringing data to our main to our system. So if we have our main memory like this, remember we had pages here and there. Maybe I can reserve this part for my page tables. So if the virtual address comes in, I first see where the beginning of that page table is. That's base register for this program. So for example, let's say this is a virtual address for program 1. So I'm going to go and find the base register for program 1, and that will point me to this point in my main memory. Then I'm going to add it with my virtual address, and that's where I'm going to go and grab this value here. This is actually the page table for this program, and that index shows which physical address it needs to come. This basically becomes the physical address of this. Then I'm going to use this physical address to address the memory again. And this time, this address would be the address that's pointed by the physical address, okay? So my virtual address goes through two steps. The first step is going through some part of the memory in order to read the page table. The outcome of that page table would be actual physical address. That physical address goes into my memory again. And at this point, I get the data that I want, okay? And if I have multiple programs, what will happen is I have multiple of these page tables. So this one, for example, would be for program number 2. Maybe this one would be for program number 3, and so on. So I'll have multiple of these base registers that points to here, points to here, and points to here. This address will be added to this to points to here, for example, or somewhere in the middle of here, or somewhere in the middle of here. I'm going to get the physical address that I want. Then I go to the main memory and read it. Question? So the question is that if the page table is stored in the main memory, do we also cache it? Good question, and we're gonna actually get to that point of do we want to cache the page tables or not? The short answer is that we're gonna have another structure called TLB to cache that, but we'll talk about. For now, think about nil. They're part of the reserve part of the main memory, so they don't go to the cache. Any other questions? All right, so let's actually kind of like, calculate quickly how large is the page table. So if we have that, addressing mode of 2 to the power 20, and if our physical addresses are 28, then basically each entry in the page table would be 28 minus the offset plus the flags. Roughly, if we have all the flags and everything, we're talking about somewhere between 25 to 32 bits or 4 bytes per entry in my page table. And then since I have 2 to the power of 20 virtual pages, we said that basically that's the number of indexes that we're going to have. So each entry is around 30-ish bits. We have 2 to the power of those. That means that for every single application, I need 4 megabytes of page table, okay? Assuming that everything is going to be accessed. And if I have, for example, 10 different applications, I'm talking about 40 megabytes of just storing the page table itself. And remember, we are talking about, for now, we are talking about 256 megabytes of main memory. So like, if I have like, 8 different applications, 32 megabytes of this 256 megabytes is just used for storing page table. Huge overhead. Right? So that's a one big problem. And the problem gets even worse if you're using 64 bits addressing mode, because then instead of 2 to the power 20, we're going to have 2 to the power of 40 or even more because we have bigger virtual addresses. So we need more rows. So actually everything grows significant, right? So this is how big the page table would be. And that's a huge problem. Okay. So now that we know that, the page table itself is storing the page table is a big headache, it's a big challenge. Let's see if there's any way that we can compress the page table. So maybe instead of 4 megabytes, we are storing 1 megabyte or even less. Let's see how we can do that. Before doing that, let's have a quick break. We come back and we will talk about it, okay? All right, let's continue. So we said that, we want the page table and we understand how do we do the translation. Now the question is, where are we going to store the page table? And now we say that, okay, we're going to have the page table stored in the main memory itself. So one bad thing that happens is we are basically, every single load now becomes 2 loads. So we are basically increasing the overhead by 100%. The second problem is that for every single page table, we need to kind of store roughly 4 megabytes of data for every program. If you have multiple programs, that's, overhead increases, okay? So let's talk about these 2 problems, the double access problem and the storage problem. And let's start with the second. Like, let's see if we can maybe somehow store less amount of data for each page table, kind of compress our page tables, okay? So what we can do to kind of compress it is similar idea that we use for page table themselves. Maybe we can store page table as page tables themselves. Let's see how. So basically, we're going to have what is called a hierarchical page table. The tip is broken. No. Anybody wants to borrow their tip or their pen? You have an extra pen? You're not using it? Thank you. Should borrow it. Okay. So we're gonna have, yeah, sorry guys. Usually this is the time that we just cancel the class and we go home. But it happens to me one time. I remember I was in undergrad and the slides didn't work. That was like one of the highlights of my undergrad. But yeah, these days, unfortunately, everybody has Apple. All right. So we're going to have what is called a hierarchical page table, which means that we're not going to like store everything in one page table. We're going to have two-step translation. So basically, remember I told you that, our virtual address has the offset part and has the virtual page number part. And then this was the part that we were going to use in order to index my page table. What I'm going to do now is that I'm going to divide this virtual page number into two parts, P1 and P2. I'm going to call this the first index, the level 1 index, and I'm going to call this one the level 2 index. What I'm going to do is I'm going to use this first 10 bits. So this would be my base pointer. This would be, for example, program A versus program B versus program C, and so on. So for each one, I'm going to have a base pointer. I'm going to add this index here to this base pointer, and I'm going to go to my level 1 page table. Within that, whatever this index says, I'm going to pick that line. And this would be basically the beginning, the base of another page table, the level 2 page table. And depending on how many indices I have here, I'm going to have that many of those page tables in second level. So I always have one table for the first that has 2 to the power of 10 entries. But then I'm going to have 2 to the power of these tables with the entries for the physical page table, right? So then I'm going to use this P2. So for example, let's say this is the value that is stored there. I'm going to use that add that with P2, and this is the address that I'm going to get as the physical page number. Okay. So this way, I'm going to get the physical page number in 2 tries instead of 1 try. And what we're going to do, what basically this gives us is, hopefully this will reduce the size of my page table because I'm kind of translating it into two pieces, okay? But the translation, I think you get. So to repeat it one more time, I'm dividing the virtual page number into 2 pieces, P1 and P2. I'm using P1 as the offset for the first table. We're going to go through that entry. That would be the base address of the second page table. I'm going to use that and then add that with the index of P2. And then I'm going to get my physical page number. And that's the translation. So the translation happens into 2 steps. Okay. And then this process, this hierarchical page table, this process of going to the first table and then going to the second table and then going to the main memory is called page table walking, or walking in general. So we are basically walking from one step to another step to another step in order to get what we want. Okay. So page table walking is this process of translating the address in multiple steps. So if you look at the amount of page table that we want in this scenario, you will see that basically this one would be has 1K, and each one is 32 entries, because this is basically the amount of virtual address, the size of the virtual address, for example, if assuming that the virtual addresses are 32. Then we're going to have 1K of these 1Ks, right? So we have 1K tables. Each one is 1K. And then each one is again 32. And then the combination of these tables all together, which is 101K basically tables in roughly, that would be basically my page table, and it's much actually bigger than 4 megabytes because we're not only have one table, but we have 1,000 of that 1,000. Okay. So the size of this is actually much more bigger than what we have. And that's not what we wanted, unfortunately. Remember, what we wanted was we wanted to have a page table that was much smaller than 4 megabytes. Okay. So what we can do instead? What we can do instead is, remember I told you that the virtual space is very sparse, that essentially we think that we have the entire 2 to the power of 32 for ourselves, when in reality, if you remember, I said that, there's different sections and only small portion of each section is really used, okay? So all these tables that we are keeping track of, many of them are actually not ever going to be used because they are pointing to a virtual address that is not used in real program. So what we can do is basically saying that if we are not going to use, if that's part of the memory is not being accessed before, we don't need to keep track of that for now. If in future we need that, we will assign a new page table for it. So at the beginning, if only, for example, 10 virtual addresses are being used, we only need to have 10 tables kind of, in some sense, to kind of keep track of that, okay? In other words, we are saying that if part of the memory has not been used, part of the virtual address space has not been used, there is no need to keep track of tables for those parts. And especially if, for example, this part, the higher bits, only, for example, 1 or 2 bits of that higher bits is being used, then basically all you need to keep track of is 2 of these tables, 2 of these rows. So for example, this row here, and this row here. For example, let's say all your addresses ends with 0, 0, 0, 0, 0, another 4 zeros, and then maybe 1 or 0. So basically only 1 bit is being used as 0 or 1 in your virtual address. The rest is always 0. So in that case, what you really need in this first table is either the first entry or the second entry, right? Either this one or this one. And then all these other entries that are always empty and invalid. So all you really need is 1 table for this and 1 set of table for this, okay? So significantly, the amount of, second level tables will be reduced because you only need 2 of these and not 1K of these. You remember, you need 2 to the power of 10 number of tables in the second level. But if I tell you that you only use 2 or 3 bits of that, you only need 2 to the power of 2 or 2 to the power of 3 of this. So we are order of magnitude reducing the size of your second level table from 1,000 to 3 or to 4 or 8 or 16 or something like that. And that's where we're going to get a significant benefit in terms of storage, because we only need to store this first layer table, that is 1K, right, entries. And then depending on how many of them are we really using, that would be our second level. So we're going to get a huge performance storage benefit in the second level by just eliminating the need for storing things. If, for example, then the second address then is used, then we're going to assign a new table and we're going to keep track of that. But as I said, since on the average, majority of, our virtual addresses is sparse, only a few of them are used and the rest of them are not used, then we can only keep track of small portion of my page tables. That's why hierarchical now makes sense, because essentially what I'm doing is that we are using the higher bits that typically are always 0 as my first round of checking. And typically, since most of them are always 0 and a few of them are only 1s, then we're gonna just keep track of those second level tables instead of like keeping track of everything. All right, does that make sense? Any questions? The question is, this relies on the fact that the program only uses certain virtual addresses. Yes, but as I said, this is the typical behavior of most programs, because not all the programs use the entire 2 to the power 32. We don't say that it's not going to happen. It might happen. In that case, you're going to have 4 megabytes per program. But on average, that's very rarely happen. Okay, that's the idea. How do I determine what? Say it again. How do we determine the number of bits the program used for virtual addresses? That's the design of the processor. For example, if you say you have a 32 bits, design, then we're saying that our addresses are 32 bits. Level 1, yeah, 10 bits is going to be used for level 1, yeah. Mm-hmm. Mm-hmm. Yeah. Oh, okay. So the question is, how does the hardware knows that when to assign these tables? Is that your question, right? So what happens is whenever you access those, the first time you're accessing those, so remember, you're not gonna read things from your memory if you don't first write to it, right? So when you're writing to it, that's when your page table will be assigned. So the new data comes in. For example, your program starts with maybe 4 pages, okay? And now for some reason, your program asks for more pages. That's when your operating system will assign new pages to you, and then they're gonna assign these new tables for you as well. So the idea is we're gonna start with smaller sizes. As the things grow, then we're gonna assign more things to it. And that's the operating system jobs to know when to assign and when to remove and so on. So at the beginning of creating a process, we're gonna create a code region and data regions and so on and so forth. At the same time, we're gonna create these page tables depending on the actual data that the process needs. That will be handled by the operating system. And then during the execution, if more data is needed, the process requests that, and then the operating system reserves some part of the main memory for it and do the translation. Does that make sense? It's more of an operating system's job, so we don't really talk about that part, but yeah. Question is, does the latency of memory access significantly increase when we are doing 1 versus 2? Yes, because think about this as every single access now becomes 1 memory access, right? So if you need to walk a lot of stages, then we are adding more memory access more. Every single one is the same, but if you do 2, it takes more time than 1. But it's kind of the trade-off that we do for getting more storage. And in modern systems, it's not just 2, there could be even 3 levels or 4 levels. So the longer we walk, the higher the latency would be. So the question is, how do we know the base pointer? Yes. So every program that creates, we know the base pointer for that. Yeah. So all the way that the initial handling is done by how do we create a process, and we didn't really talk about it in this course because it requires an entire lecture about what is process and so on. So you will see it in 111L if you take it, or you can just read it for yourself. So the question is, why only 2 levels? We can do more. 2 is the minimum, right? But you can do 3 or 4 levels as well, because the more helps you in some sense. But remember, it's still a trade-off, because more levels means more access latency. So it's kind of like a diminishing return at some point. It's at some points your access time grows significantly. Because you only save if you have sparsity. If you have many, then the chances of having sparsity decreases. So we won't actually save that much. Okay. So it's kind of like, just to summarize on what we said, we use page tables for address translation, page tables are large, so we should find a way to fix it. And we use hierarchical page tables and the concept of page table walking in order to fix that issue. The idea is that many of the virtual addresses won't be used in real programs, and that's why we don't need to keep track of all these many pages inside our page table. So this way we can only keep track of some of the page tables, okay? But now let's talk about the second issue that I told you, that we need double access. And now with hierarchical page table, we need 3 or 4 accesses, consecutive accesses to just read one part of the data, right? So, that's a big issue, especially if you think that, you know, accessing to the main memory takes a lot of time, right? So it takes hundreds of cycles to just read one time. And now we are saying that for reading a memory with hierarchical page table, you need 3 accesses to kind of, you know, access your memory. So what we can do in order to fix that issue, what we can do is, somebody's talked about the caches. We can cache the translations. So we don't need to go through the page tables and then walk on the page table and get the value and then go to the main memory. If I somehow cache the physical page number somewhere, so that if the virtual address comes, I'll just quickly tell you this is your page number without actually going to your main memory, then your access time for reading that physical page number is same as accessing your L1 cache or L2 cache, okay? So if we can quickly cache that, then I'll have that problem fixed, okay? And that's actually what is very, very extensively used in modern systems. And we call that translation look-aside buffer, or TLB. So what the TLB does is basically, instead of like translating the address for you, it first goes to your TLB, to your cache, and see whether that address has been cached or not. Of course, since we are talking about cache, not everything can be cached there because the cache storage area is limited. So we only have maybe 64 or 128 or something like that. That's the number of entries that we have on that TLB. But if your virtual address happened to be on that cache, then you don't need to go to your page table at all. You just can look for it in that TLB, get the physical page, and then just directly go to your main memory to get the value that you want, okay? So what we're gonna have is, we're typically gonna add what we call a memory management unit, or MMU, that sits between your CPU and your memory. And the first thing that it does is that, so remember, at this point, you have your virtual addresses. At virtual addresses, the very first thing that you do is just looking at your TLB to see that whether that physical address is there or not. If it's there, then you have your physical address, then you can go to your cache and you can go to your main memory. Because remember, everything in your cache and everything in your main memory is physically addressed. You cannot use virtual address to access anything, okay? So the first thing is the translation for both these cases. So if it's there, you get your physical address and you do whatever you were doing before. You go to your L1 and L2 and main memory and you get everything that you want. If it's not there, if it's a miss, then you have to do the physical address translation. You have to go to your page table, which is inside your memory. You have to go and bring things from your memory. And then once you have that, then again, you will have your physical address. And then you are happy, and then you can continue, okay? So TLB is the first thing that you need. You need to do your address translation first. Then you are in the physical world. Then you can access your caches and so on and so forth, okay? So what is the hit time with this? For example, if you're talking about L1, now our hit time is kind of serialized, right? Because so I need to first go to my TLB. Best case scenario, there will be a hit in my TLB. So to find the information in my L1, the best case scenario would be a hit in TLB and a hit in L1. So my hit time is combination of TLB and L1. And that's why the hit time for TLB is very, very important, okay? So it's as important as your L1 and L2 and L3 because it basically added to all of those things, okay? So how do we actually create a TLB? So basically TLB, think about it as usually a fully associative cache. What does it do is basically you do your virtual page number, right? Since it's a fully associative, you don't have index, you typically have just the tag, okay? So you basically, the tag in this case would be the virtual page numbers, and then you store your physical page number along with your tag. That would be your data store and tag store. So if it's a match, then you will have your page number and then you're done with it, okay? So your TLB is basically a table with multiple rows. In each row, you have your tag and you have your physical page number. Your virtual page number comes in. You're going to compare it with these tags. If it's matched with one of them, then you will get your physical page number, and then you don't need to go to your page table anymore. If it's not matching with any of those, then you need to go to your page table and do the translation. Question? So the question is that for different programs, the same virtual address might point to, sorry, you might have same virtual page numbers for different programs, right? So you might have what we call aliasing problem. What you will do is that in your tag, you usually also stores the program number with it. So basically, whenever the request comes, you say it's program 1, the PID, usually the process ID number, and your virtual page number. So this is unique. So even though your virtual page number is 00, for example, for both requests, this one is coming from process 1, this one is coming from process 2, so they're not the same. Or another thing that you can do is that you can divide your TLB into multiple sections for each of these so you can partition that as well if you want to. And other questions? Okay. So how do we design our TLB? TLBs usually should be very, very small. The reason that it needs to be small is that the hit time should be really, really good, should be really, really low. We usually use fully associative because we want to use our TLB as much as possible. And typically, we don't have that much locality in TLB, unfortunately. So what you want to have is like being able to very quickly find all the things that you want. And then your locality, your spatial locality is coming from the fact that you're using 4 kilobytes of pages. So within each page, you will have spatial locality. Outside the page, necessarily, you don't have any spatial locality. That's why you want to use probably fully associative, okay? If you want to use larger TLBs, then you can use things like set associative and so on. So there's nothing prevents you from having a set associative cache in TLB as well. The same story of replacement and all those things happens here as well. So as I said, usually we use fully associative, but you can use direct map or set associative as well. You can have multiple levels for TLB as well if you want to. Same story with the caches. You can have L1 and L2 TLBs if you need to. And you can have different replacement policies. Since you don't probably have much locality, it's better to have something like a FIFO or a random replacement policy, because LRU probably doesn't do well in TLBs. Okay. There's also a concept called TLB reach. The TLB reach means how many entries can I save in my TLB times the size of the pages, and that would be the amount of main memory that I can store all at the same time. For example, if I have 64 entries and 4 kilobytes of cache, 4 kilobytes of page, then my TLB reach is 256 kilobytes. It means that this amount of main memory I can store in my TLB. And remember, TLB performance is really, really important for us because that's added to my L1 cache hit time, added to my L2 cache hit time, and so on and so forth. So this basically says that if your programs needs less than this amount of main memory, then you are very, your performance would be really, really good. If your program needs more than this memory, then you will have some TLB misses, and then you will have problems with translation, and you have to wait and wait and wait for the address to comes back. Okay. So now that we know about TLB and page tables. By the way, if the TLB is not there, we're gonna call it the TLB miss, and you have to go to the page table and find that. Okay. So we're gonna have either TLB miss or TLB hit. If we have a TLB hit, then we're gonna either have a cache miss or cache hit. Then if you have a cache miss, we go to the main memory, we bring the data, and that will be the longest time it takes to have that data from our main memory, right? So now let's quickly talk about the disk as well and see what about the disk. Yeah, question. The question is that since we need to access TLB before the cache, does that mean that the size of the TLB has to be bigger than the cache? Why the size of the TLB has to be bigger than the cache? If So the question is, if you have more information in your cache than your TLB, then it doesn't make sense to have a cache because you have to go to your main memory. Remember, the TLB is storing things in 4 kilobytes versus your cache storing things in block, which is like 4 bytes or 8 bytes. Okay, so rows in the cache storing much less amount of data compared to the rows in your TLB. So in reality, what you're gonna have is your TLB reach gonna be much big, like 256 kilobytes or whatever, right? And in like modern system, this would be much bigger than this. Okay, so yes, essentially what you want is the time it takes for translating the address should be less than what it takes from going to the cache. Otherwise, it doesn't make sense. That's right. But again, remember that TLB is working on the page size level versus cache is working on into byte size level. So huge, 3 order of magnitude bigger, just with the same number of entries. All right, so let's see how we actually combine the disk with our main memory. So as we said, the disk is our secondary storage unit in my main memory. It's much bigger, but significantly slower than the main memory. Sorry. So the question is, how do we efficiently use this? Because what we want to do is ideally read everything from my DRAM and not read things from my disk, right? So let's see how we actually use that. So we use this technique called demand paging, which means that whenever a page is needed from my disk, I'm going to swap that with an existing page into my memory. So what I'm going to do is that I'm going to fill my main memory with all the pages that I want. And then if the page that I want is not in my main memory, all I need to do is kind of finding a candidate in my main memory at one of the pages that I no longer need, and go to my disk, find that page that I need, and swap these two so to get the new page from my main memory, from my disk, okay? And if you think about this is very, very similar to the idea of a caches and my main memory. In my caches, I'll also fill the cache with data that I want. If the data is not there, what I had to do was finding a candidate for eviction. I evict the cache from my, I evict the data from my cache, and then I go to my main memory and bring that data and put it in my cache, okay? So the same thing happens here, and we call this swapping or demand paging, okay? So think about that, your storage is M, which M is basically a combination of C and C, which is the DRAM, and D, which is the part of the disk. The most frequently used pages going to be stored in my DRAM, and we call that C. And M is a combination of D and C, which is the entire memory that I have. And then we just keep the rest of the pages in my main memory if the data is really not. I think today it's not a good time to teach.
I guess we really have to cancel the class, guys. I'm gonna give you that. We have like 10 more minutes, so I'm gonna just pause here. Yeah.
So next time we're gonna talk about the demand paging, the rest of the cache, the rest of the main memory design, and then we're gonna finish the virtual address discussion. Okay.